Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. We're continuing our work with logic gates, truth tables, and boolean expressions. And in this video, we are looking at minterms and explain what they are and how we find them from a truth table. And we're going to use those minterms to generate a boolean expression that is valid from a truth table. All right, let's get started. Minterms. Okay, so before we even get started on what minterms are, I want us to keep in mind this idea of thinking ones. So let's generate a truth table here that we can work with. And we're going to have X, Y, Z, and F. Let's make these a little bit longer. Great. Since we have 3 input variables, that means we're going to have 8 rows. And I like to do this divide into method here for drawing my truth tables. I think it makes it fast and pretty even. So then the least significant bit on the input, here's Z, we're going to alternate 0, 1, 0, 1, 0, 1, 0, 1. And then on the Y, we're going to alternate by 2s as we go up in significance, and then alternate by 4s. This will give us a count, and we'll see that's going to be important later on. Is it going to count up from 0 to 1, 2, 3, 4, 5, 6, 7 in binary. And let's go ahead and make ourselves a function here. Let's see, I want 0, 1, 0, 1, just like that. Okay, so that's our output function. So we want to write a function f, and we'll call that f1, that is going to be valid based on what we see here in the truth table. And so one thing right away that we're going to be interested in is the rows that have an output of 1, because that's what we're trying to achieve, an output of 1. So when do we get an output of 1? And I'm going to circle these input combinations that cause us to have an output of 1. So these are the values of X, Y, and Z that will cause an output of 1. I'm going to call those rows A, B, and C. So essentially we want rows A, B, and C, A, B, or C, I should say. Those are the ones that will give an output of 1. So if either A's input comes in, that's input sequence where X is 0, Y is 0, and Z is 1. Or if B's input sequence comes into the digital circuit where X is 1, Y is 0, and Z is 1. Or if C's input sequence 1, 1, 1 comes into the digital circuit, in either of those 3 cases, we want our output to be a 1. And so we can see in that discussion, we want either row A activated, row B activated, or row C activated or selected. And so I can write this expression sort of like this, A or B or C. And we're talking about an OR here. And the OR is permissive. So it allows things to happen quite easily. In any case, if A turns out to be a 1, then the output's a 1. If B is a 1, then the output's a 1. Excuse me, it doesn't matter what the other variables are. And so it's very permissive in that way. But there's a problem, because if I'm permissive, we might get an output of 1 for one of these rows that shouldn't be a 1. So we might have the sequence 0, 1, 0 come in, and that will also give a 1 where it should just give a 0. And so now we have to be selective. And the selective operator is AND. And so we want this A to only be 1 when the specific input sequence X equals 0, Y equals 0, and Z equals 1 comes in. Okay, so only that should give a 1. So we want to guarantee that this has to be true for A to be a 1. And we do that by writing a sequence of an and with the variables x, y, and z. So we go x, y, and z. Okay. So this is an and. It's very selective. It's only a 1 if all three of these are 1s. But our input sequence aren't 3 1s. Our input sequence is a 0, 0, no 1. And so to make sure that this term is all 1s, and that would be an and that would have an output of a 1, we have to invert the x and the y. Now remember, I said think 1s, and so we've been thinking 1s. We've been selecting the rows that have an output function value of 1. And now when we select our input values, if it's a 1, we leave it alone, but if it's a 0 in that row, as this is 0, 0, 1, then we invert it to make it a 1. So now this will evaluate to 1 and 1 and 1, and so it evaluates to a 1. So this is what we want for A. So this will select, or this will say that if this sequence comes in, if 0, 0, 1 comes in, this term A will be a 1. And that means since this is OR and it's permissive, that means the output will be 1, which is what we want. But it says that if any other sequence comes in, if 0, 0, 0 comes in, then Z is a 0, and this is a 0 in total, because AND needs all three to be 1s. If 0, 1, 1 comes in, then we have a Y of 1, it's going to be flipped to 0 because of this invert. And so then this is going to be a 0 for A, which means that this whole thing is 0, right? So the only case where this is going to be a 1 is if this input sequence is 0, 0, 1. And that's a really important part of this to understand, okay? So what about B? So B is the situation where X is 1, Y is 0, and Z is 1. But in my term here, X, Y, Z, I want these all to be 1s. And so X and Z are fine, they're already 1s, but Y is a 0, so I have to flip it to a 1. And so now when this sequence comes in, 1, 0, 1, this term, X, Y bar Z, will be 1 and 1 and 1, and so that will turn into a 1, which will make the whole function a 1. So that satisfies this being a 1, right? So we're doing this last term to kind of get those 1s. And then what about C? Well, C is all 1s. So if I have a term that just looks like X, Y, Z, I don't have to do anything to them because I'm thinking 1s, and these are all 1s, and so this will generate a 1 on the output, okay? So let's substitute these A, B's, and C's into our final expression. And so we get that F1 is equal to X bar, Y bar, Z, or X, Y bar, Z, or X, Y, Z. Now this will ensure that we get a 1 if row A is selected, we get a 1 if row B is selected, we get a 1 if row C is selected, but in all other cases, we'll get a 0. And that's how we use minterms. So these are what we call the minterms. Okay. So let's define then what makes a minterm, right? So a minterm selects one row of the truth table. A minterm includes all the input variables. In this case, every single term has X, Y, and Z in it. X, Y, and Z, X, Y, and Z. So it's either complemented or not, but includes all of the input variables. And it's an AND term where let's see, if the input is 1, the variable is uncomplemented, and if the input is 0, actually here I'll just do 1 and 0, the variable is complemented. So that is what we did, if that's a little confusing. So we saw that we had to complement x because the sequence that we wanted to select was 0, 0, 1. We had to complement y because y was 0, but we left z alone because z was 1. Okay. So that is what we kind of some of the bullet points that we want for a minterm. I think of a minterm as a row selector. So it selects a row where the output is 1. We want to select rows where the output is 1. All right, let's do a second example. So I'm going to build another truth table here. Drawing skills. Should have some like hold music right here. La, 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 la. That's like the Jeopardy music. Okay, so we got X, Y, Z, and we'll call this F2. And again, building this truth table, I think this is valuable to see it again. We alternate by 1s, then we alternate by 2s, and then we alternate by 4s, and then we alternate by 8s, and then 16s. And so this one we're going to go 1, 0, 1, 1, 0, 0, 1, 0. Okay, great. And so this is a count. It counts 0, 1, 2, 3, 4, 5, 6, 7. And this time I'm just going to kind of write that here. 0, 1, 2, 3, 4, 5, 6, 7. So we can sort of reference the row by the binary number that the input sequence would represent. And so 0, 0, 0 represents 0 in binary. 0, 0, 1 would represent 1 in binary. So we have the 0th row all the way to the 7th row. Okay. And so again, I want to select the rows where the output is 1 and take a look at their input sequences. Once you get good at this, it's pretty fast to do this. And so this time I'm going to go directly to writing the expression. So F2 is going to be, well, we have X, Y, and Z. Here's a little shortcut. We know it's going to be ORs between X, Y's, and Z's. X, Y, and Z, every single one of these terms is going to have X, Y, and Z. So I have 4 rows, so I need 4 terms. And now I have to select if I invert or not. So what are we thinking? We're thinking 1s. And so if it's a 1, leave it alone. If not, flip it. So this input sequence is 0, 0, 0. So we have to flip them. So this makes them all 1s. This input sequence is 0, 1, 0. So we have to flip the X and we have to flip the Y, or sorry, the Z. That makes this all 1s. This is 0, 1, 1. So we flip X. This is 1, 1, 0. So we flip Z. And that's it. We're done. This is the minterm expression, sum of products expression for this truth table. And this is a valid Boolean expression that will allow us to implement a logic gate network that will affect this truth table and its functionality, which is really, really, really cool and really easy to do. So just wanted to point that out. Okay. So let's move to another way that this is represented, and that's using the symbols M. And so what row is this first minterm representing? Is it selecting? That's the first row in the table, which we call row 0, because that input sequence represents the binary number 0. So we can call that M0. What about that second one? We can see that's row 2, and then row 3, and then row 6. So this is sort of a shorthand version of writing the above expression saying, hey, I understand that you know how to do midterms. So let me just give you the fact that it's midterm 0, 2, 3, and 6, and then you can go from there. There's one more way that this is done, and that's using the sigma operator, okay? And so this is the sigma of m, and then you do 0, 2, 3, 6. And so these are all of the m's, 0, 2, 3, and 6. Those are the ones that we use. I think I got that. Part of my brain says that I have that wrong in some way. So if I do, you can scream at me in the comments. But the idea is there that you use the sigma of the m's, 0, 2, 3, and 6. Add those up. So I see that less and more of these two in my experience. Okay, a little long-winded there. Hopefully, though, Minterms is a little bit difficult to understand at first look. I hope that made sense to you and that you enjoyed it to some degree. I'm Mike Stanzik. This is Digital Electronics Classroom. Thanks a lot for watching and have a great day.